Okay, good. So it looks like we're recording now. Today's class is going to be about we're going to be talking about the energy band diagrams of MOSFETs and how to calculate the threshold voltages of MOSFETs. Okay. The slide that you're seeing up. Let me share my window here so everyone can see. Okay. So hopefully everyone can see my screen now. Give me a thumbs up if you can.
Yep.
Okay, great. So today we're going to cover the slide that you're seeing up here is just some review from last time. I want to just quickly go over the key concepts, the intuition behind how a MOSFET works, specifically in how it creates a conductive channel, and then we'll get right into the energy band diagrams of a MOSFET, which is something that you'll be expected to be able to draw for the exam. So let's quickly go over this again. You see some of the scrawling on that was from the previous lecture. The key part about a MOSFET is that it is an electronically controlled switch. And an electronically controlled switch, it can create a conductive channel between the source and the drain, or it can turn off the conductive channel between the source and the drain. And it does that by applying a gate voltage. All right, rather than like a mechanical switch where you have to move it on and off to the on or off position, the MOSFET is a type of switch where you can, by applying voltage to the gate, you can turn the switch on or off. And the way that it works is that you have your source and drain regions. Let's say the source and drain regions are N-type, and the gate region is originally a P-type. If it is P-type now, you have like an NPN type thing. You have back-to-back diodes. So if you try to flow current in one direction, one of the diodes is reverse biased. If you try to flow current in the other direction, one of the diodes is reverse biased. So essentially no current can flow between the source and the drain. But if you switch the gate from a P-type to an N-type material, as you can see on the bottom here, then you can have current flow between the source and the drain. Okay, and that was the key concept. And the question that we're going to focus on today is like, how do we actually invert this gate region from a P-type to an N-type? So that's why it's called a field effect transistor, because there's a field effect that switches this from P-type to N-type. And we're going to be talking about the energy band diagrams today, which describe that sort of operation. We quickly describe what's happening physically, just to remind everyone of the intuition. You have this, the structure. You have like the source and drain regions out here. You have a P-type substrate. You have an insulator that's typically like a silicon dioxide. At least the standard ones are. Like the newer ones have higher K dielectrics, which are used. By applying, and this is the metal or polysilicon gate material, which goes right on top of the oxide. The way that you invert is you apply a positive gate to source voltage, and that gate to source voltage builds up positive charge on the gate material. Okay, the substrate is grounded, so this kind of looks like a capacitor. You're applying a voltage between the gate and the source, which is equivalent to a voltage between the gate and the substrate here. A positive charge builds up on the gate. Electric field pushes into the P-type substrate. The holes get pushed away by the electric field, and the electrons get pulled in by the electric field. And so then you create, the electrons are responsible for creating this channel. It's inverted because if you have a high concentration of electrons, you have an N-type material. If you have a high concentration of holes, you have a P-type material. So this electric field, the field effect, has created or inverted the material from a P-type to an N-type just right underneath the gate. And we're going to talk about the charge distributions, how to actually calculate the charge distributions and depletion charge in this type of situation. So last time we just talked conceptually about what happens, and now we're going to get more into the specifics. I'm going to skip over the stuff on the triode region and saturation because I want to get into the material that we're going to cover today. All right. So we did derive the current equations for the triode region. One of the things that we found out is that the strategy was to split it up into split the conductive channel up into small pieces, create a differential equation which describes the I versus V relationship in each one of those regions, and then integrate both sides and to come up with the current equation in the triode region. We also found the resistance in the triode region, the current in the saturation region, and then finally we ended off with this slide where we were looking at the IV characteristics in the PMOS and the NMOS devices. Okay, so when you look at some of these curves, what you'll see is these, initially the current goes up almost linearly at the beginning when you're at small values of VD. So that's when you're in the triode region at low VD. It actually has almost a linear IV characteristic, so it kind of behaves as a resistor. As you increase your drain voltage, you increase it, and then the current starts to level off. It starts to become horizontal. So the point where it becomes horizontal is what's referred to as the saturation region. This typically happens when the drain to source voltage, VDS, is greater than VGS minus VT. And we talked about that on the previous slides. All right. So at that point, there's a phenomenon called pinch-off that happens that prevents the current from increasing much with any change in VD. So here it's behaving in the saturation region, it's behaving as a current source. A current source always delivers a constant current regardless of the voltage. At low values of VD, when it's in the triode region, it's actually behaving as a resistor, where my mouse is right here. And in the middle, the transition region, that's where the IV characteristic is nonlinear. It behaves almost like a quadratic function, has a quadratic element to it, and that is the top end of the triode region. Okay, so an enhancement mode PMOS device is exactly the opposite. I hope some of you had a chance to perhaps consider like what the electric fields are, what type the inversion channel is, and so forth. Very similar to the NMOS device, except everything is inverted. Instead of applying a positive gate to source voltage, you apply a negative gate to source voltage, and the inversion channel here is a P-type material instead of an N-type material. And as I think I mentioned this in class last time, since we emphasize the NMOS device, sometimes what I do is I ask on exams, I often ask students to figure out some things related to the PMOS device, because that allows me to test your understanding of the central concepts. If you can take the concepts of an NMOS, apply them to a PMOS, then in my opinion that you've understood it fairly well. So I'm giving you a big hint here that, spend some time figuring out the PMOS device based on what you've learned on the NMOS device. Okay, the performance, the IV characteristics of a PMOS device look like this. You can see it's the mirror image of the NMOS device. You notice that these numbers here, which is the gate voltage is negative because you're applying a negative VGS instead of a positive VGS. And the current is also negative. The current flows from source to drain instead of from drain to source. All right, and this is just a summary of the enhancement mode and depletion mode NMOS and PMOS devices. Now, we talked about the enhancement mode device. So the enhancement mode device, the reason why it's called enhancement is because the device is normally off. Okay, so if you don't apply, here's the definition of enhancement mode devices is as follows. You can jot this down on your slides if you'd like as well. An enhancement mode device is off when there's zero voltage being applied to the gate. Let me grab my pen real quick. I want to write that down. Okay. All right, here we go. Enhancement mode. Enhancement mode device means that device is off when no gate voltage is applied. All right. So another terminology for that is that we say it's normally normally off. So, if some of you have worked with valves before, when you're designing, various types of systems like fluidic or gas valves, this terminology of normally on and normally off often applies to fluidic and gas valves. So the enhancement mode device is typically off when no gate voltage is applied. The depletion mode devices are the opposite. They're normally on. Right? I'm highlighting that with the pen here. They have a conductive channel even when there's a zero gate voltage. All right. So what that means is that, if we were to draw what this type of device might look like, let's say you have an NMOS device like this. It's a P-type substrate. You have your gate and your metal here. So a depletion mode device will actually have a conductive channel. It'll actually have a conductive channel even when there's no gate voltage applied to it. Now you might be wondering how can you create a conductive channel when you don't even apply gate voltage to it? We'll get into that in some of the slides when we get into the energy band diagrams and when we calculate the threshold voltages, and you'll see mathematically that it is possible to have a gate, a threshold voltage which is actually negative. So you can see for an enhancement mode device, the threshold voltage is positive for an enhancement mode device, and it's negative for a depletion mode NMOS device. Physically, what happens, I can tell you, is that because of the metal and semiconductor work functions, the bending of the band diagram can create a situation such that you can even have an inversion channel even when zero gate voltage is applied. Okay. An enhancement mode PMOS device, as you know, the threshold voltage is negative in a PMOS device, but in a depletion mode PMOS device, there's a conductive channel already present. In that case, the threshold voltage is actually positive. So if a device is on with zero gate voltage applied, then what you have to do, if you actually have to apply a negative gate voltage to turn the device off. Okay, it's like if you think about this as a switch, it's a switch that's always in the on position. You actually have to apply voltage to turn the switch off. That's what a depletion mode device is. An enhancement mode device is if you don't apply anything to it, the switch is off. You have to turn on the switch. You have to apply a voltage to it. Okay. All right. And these are just some of the. Yes. Go ahead, please.
Lemma cannot hear you.
Oh, Lemma is not able to hear me. Okay. Let's.
Sorry, I interrupt you.
No problem. I'm glad. Thank you for that. Can everyone else hear me? Please give me a thumbs up on the public chat if you're able to hear me. Okay. So Lama, if you're not able to hear me, is it? Oh, okay. David says he also lost audio for a second and had to relog in. Seems like the majority of folks is able to hear. So Lama, could you check your device to see if maybe there's like a volume, if you can increase the volume or something like that? Oh, okay. Jacob also says he has to relog in. So, Lama, why don't you try that? Try to log out of the conference and log back in. See if that helps. Otherwise, just try increasing your volume and see if that helps as well. Okay. All right. Then I will just go ahead and continue. So now we're going to get into calculating the MOSFET currents. This is something I asked everyone to do just on your own. I'm going to post a homework problem today that pretty much you're going to do exactly this. So please make sure that you can do straightforward problems like this. It's an easy way to get points on the exam. These problems are pretty straightforward. The more tricky questions would be questions on the conceptual things. Yes?
Can you go back to the previous slide real quick?
Sure. Okay. This one? Or this one?
The one with yeah, that one.
Okay.
Are all the gate voltages supposed to be applied positive? Oh, I see. Never mind. I see.
Yeah. So with the gate voltage that we're talking about, yeah, the NMOS devices, you typically apply a voltage between the gate and the source. So VGS is positive. And in the PMOS devices, you apply a voltage between the source and the gate. So the source to gate voltage is positive, and VGS is negative.
Right. Yeah, I got it. I didn't see the S and G had switched at first. Yeah, I got it now.
Yeah, no problem. So we could also put here a negative VGS because we've been saying that the PMOS devices have negative voltage associated with it, negative gate voltage. All right.
Thank you.
Yep. So the answers for the questions are on here, so you can test yourself and see if you can get it right. Okay, now we're going to talk about the energy band diagrams. Okay, we're going to spend a good chunk of today's class on this. So what we're going to do here is we're going to draw the energy band diagram in the vertical cross section. So if we think about the device, I'll draw it again up here. Let's say you have an NMOS device like this, P-type substrate down here, and then you have your gate up here. Okay, when we were doing diodes, let's say we had a P-type material and an N-type material. Okay, we were drawing the energy band diagrams with the X position was going from P-type material to an N-type material. So we were drawing the energy band diagram as you transition from the P-type to the N-type material. Here, when we're referring to a vertical cross section, we are referring to this direction, the vertical direction. So the vertical direction, we're going to have a metal, and then we're going to have an oxide, and then we're going to have a semiconductor. All right. And that's what's shown here. So this is the gate metal. This is the oxide just below the gate metal. And this is the semiconductor just under that. Okay, so we just want to make sure everyone's clear that we're doing a vertical cross section here. All right, and this example that we're doing is an NMOS device. So it has a P-type substrate. All right, the first thing we're going to do is equilibrium. Equilibrium means that there is no voltage applied to the gate, and we are going to assume that this is an enhancement mode device. An enhancement mode device, so I'll put this here, just so we're totally clear, enhancement mode. Enhancement mode device, there we go. Enhancement mode device at equilibrium. Okay, so the device is going to be off. We know that already. So what we're going to do is draw the band diagram for it. So just like we've done before, hopefully you have a set of rules in your head on how to draw band diagrams here. So the first rule that you want to remember is that at equilibrium, no discontinuity or slope can appear in the Fermi level. So we just draw the Fermi level as a straight line across like this. Now notice that one thing I've done here is that the oxide, we don't bother drawing the Fermi level in the oxide material. You can if you want, but we generally just leave it out. I'll get to why that is in a second. All right, so the Fermi level goes in a straight line across like this. You have the Fermi level in the metal, and then you have the Fermi level in the semiconductor. So the next step is to draw the metal on the left-hand side of the diagram. And with the metal, you know that the metal only has the Fermi level, and then it has the E0, the vacuum level. Okay, so E0 and EF, we draw that here. Okay, you draw E0 up here, and the way that you know the distance between these two is you're told, you'll be given on a problem what the metal work function is. And typically the metal work function is obtained using experiments, like physics experiments. Does anyone remember, let's see if anyone remembers, what experiment is used to find what the metal work function is? Let's see if anyone remembers. You can just put it in the chat if you like, or just blurt it out. It's something we went over in module 2. So one guess is a photon. It's close. Actually, a photon is involved in this experiment. Does anyone recall what the name of the experiment is, or what the name of the effect is?
Photoelectric effect.
Photoelectric effect. There you go. Yeah, that's what we're looking for. Remember, the photoelectric effect is where you take a photon, and you shoot the metal with photons, and you keep on increasing the energy of the photons until you start ejecting electrons from the material. That energy at which you start ejecting electrons from the material, that is the metal work function. All right. So this is the metal work function. It will be given to you in the problem. So you have your E0 up here. Then you draw the you draw the oxide material next. So you start off with the metal, then you draw the oxide. So with the oxide material has an E0. But we don't put the EF in there because an oxide material, there's really no carriers in it. If you remember what the band diagram for an insulator looks like, in an insulator you might have a band up here and then maybe a band down here, but there's a large gap between them, and the Fermi level might be somewhere between that gap. And the gap is very large. As a result of that, there's no carriers in an insulating material. So that's one of the reasons we're not really concerned with what the carriers are doing in the oxide, because the oxide doesn't have any carriers, or it has such an incredibly low concentration of carriers that we can ignore it. So what we do instead is that we just draw the E0 for the oxide. So the E0 lines up like this with the oxide, and then we draw vertical lines here to represent the fact that the oxide has just a bunch of area here where there's no energy states, 0 energy states. So in the band diagram for an insulator, there's a lot of room above and below the Fermi level. Above and below the Fermi level where there are no allowed states. So this band diagram just appears blank. So the right side of the diagram is the semiconductor portion. You know how to draw that already because we did something similar with the metal semiconductor junctions. What you want to do is when you draw, you have your EF here, and based on the doping, you know the distance between EF and EV. So you know that the distance between EF and EI. You know this distance here. So that's what basically allows you to line up the diagram with the left-hand side. Okay, so I want to make a point here that the way that we lined up the right side of the diagram is that you can draw EI first, because based on the doping, you know the distance between EI and EF, and then you go ahead and draw EC, EV, and then you can also draw E0. Now what I've drawn here is a special case where the semiconductor work function and the metal work function are the same. Now I want to make sure everyone knows that this is not normally the case. There's usually some difference between the phi m and phi s, but just for simplicity's sake, we're assuming that they're the same here. Okay, so you draw the p-type material on the right. The position of EC, EV, and EI depends on the doping and the band gap. And then the final step that you do is that you can draw a line connecting E0. Now in this case, like the E0 and the oxide just directly connects these two together, and the E0 happens to be at the same level. The Fermi levels are lined up, and the E0s are lined up. This only happens when phi m is equal to phi s. Okay, it's the simplest of cases. And what you notice here, the key feature that you notice here is you see that there's no bending of the band diagram anywhere here. Okay, so in this type of situation, we think about, this is the electron affinity there. We think about what the holes are doing in the substrate here. Remember that there's, in a p-type substrate, there's a lot of holes and very few electrons. So we're going to be more interested in what the holes are doing. And you can see that the holes are down here. The EF is closer to EV, so there's a lot of holes. There's very few electrons. There's no bending of the diagram, so those holes aren't really going anywhere. They're not doing anything. If you want to get the holes to move, you either have to have a situation where there is diffusion or drift. So, if you think about it, the holes, there might be some holes over in the metal, but this oxide is creating this barrier that prevents any diffusion from happening. On the other hand, and at the same time, there's no slope in the band diagram. There's no slope to EV. This is just a horizontal line. So that means there's no electric field. And as a result, the holes are, there's nothing to cause them to drift or diffuse. So the holes are stagnant in this case. So the behavior of the material here is that your metal is a metal. You have the oxide here, and your semiconductor is p-type. There's no inversion channel here. There's no depletion region formed here. It's just a p-type material. Any questions here? Okay. So the thing that you will want to be able to do for the purposes of this class is that you will want to be able to draw these types of energy band diagrams. So I suggest just going through the steps and feel comfortable drawing the band diagrams. In your homework, there are going to be questions where I give you phi m and phi s and give you the doping of the semiconductor and so forth, and tell you to, ask you to draw the energy band diagrams at equilibrium and some of the other regions that we're going to talk about. So key thing here is to practice. I know it looks very easy when it's just up there on the screen, but just to make sure that you know it, make sure you can do it on your own. All right. Now, this is, you can think about ways of interpreting the energy band diagram. This is the same diagram that was shown before, but just in a more static format. So you can see here that the phi m and the phi s were equal to one another. There's holes in this region of the semiconductor, but the holes have this barrier that prevents the holes from moving into the metal. The barrier also prevents any charges from moving into the metal, into the semiconductor. All right. And this, you can think about this as corresponding to a physical model too. Like if you have an oxide material, if you have an insulating material, current doesn't go through insulating materials. So in the energy band diagram also, the fact that you have these large barriers here that prevents charges from going back and forth, that makes sense. It corresponds to the physical model. All right. So let's move on and talk about the accumulation region. So the accumulation mode refers to a mode where you're accumulating majority carriers under the gate. And the way that would be done in an NMOS device is to apply a negative voltage on the metal. Okay. Now, I just want to make sure everyone's clear on this. We are applying a negative voltage on the metal. Typically, what we would want to do in an NMOS device, if we want to turn the device on, we typically would apply a positive VGS, a positive voltage on the gate metal. Okay, here what we're doing, the accumulation mode happens is when you apply a negative voltage on the gate for an NMOS device. Okay, so this is your metal work function here. This is your semiconductor work function here. So this was the band diagram at equilibrium. This is what the equilibrium band diagram looks like. And what you'll see is where I'm just going to animate here and show you how the band diagram changes when you apply a negative gate voltage. So the rule is this. You all remember this from the diode chapter. If you apply a negative voltage on the metal, the Fermi level on the side of the metal goes up. Right? So whatever side of the band diagram you apply a positive voltage to, that side goes down relative to the other side. So we're applying a negative voltage on one side of the diagram. That causes the Fermi level to go up in relation to the other side. So this is what the metal side looks like, and what we're going to do is we're going to move the right side of the diagram down. Okay, so just, you can see this as it animates. It's like if we apply a negative voltage on the metal, the right side, the opposite side of the diagram goes down. So now we have to look at, I'll just show this to you again, so for those of you who missed it, look at the right side of the diagram here and just imagine the right side getting pushed down. So you have a difference in Fermi level here, and that difference in Fermi level is proportional to how much voltage that you applied. So when the right side of the diagram goes down, now we have to do band bending. All right, band bending, the phenomenon of band bending, it occurs because the conduction, valence, and vacuum bands, so E0, EC, and EV, they have to be pseudo-continuous. Okay, in this particular case, since both sides, the metal and the semiconductor, they both have the vacuum level E0, you can't just have an E0 here and then have a sudden discontinuity in E0 here, where my mouse is. You can't have the sudden discontinuity. The bands have to be continuous. So what happens in the semiconductor, the band bends up like this. Okay, so it bends up to meet the E0 in the oxide and the metal. Okay, so when E0 bends up like this, EC, EI, and EV, all three of them bend up again like this. So again, to show you, the E0, it bends up, and so does EC, EI, and EV. Okay, so this is just a rule for an energy band diagram. What's actually happening physically is that when you apply a negative voltage to the gate, okay, I'm just going to draw this down here. Imagine that you have an NMOS device here. All right. So I'm going to pose this as a question. This is your P-type substrate. All right, let's say we apply a negative VGS. So we apply a negative voltage to the gate relative to the source and the substrate. What kind of charges are we going to build up on the top of the gate here?
Negative.
Okay, negative charges build up on top of the gate. Which direction is the electric field going to be pointing?
Towards the gate.
Right? So your electric field is pointed in this direction. So if the electric field is pointing in this direction, you have holes and you have electrons in the substrate. So which direction are the holes going to go?
With the field.
Got it. So you're going to have a buildup of holes here, and you're going to actually push away the electrons this way. All right. So the accumulation region, the accumulation mode, let me just make this larger so everyone can see. In the accumulation mode, you've applied a negative potential on the gate. So you have a negative charge on the metal, and then you end up having a positive charge on the opposite side of the gate. So that electric field, it pulls in the positively charged holes, it pushes out the negatively charged electrons, and so you've accumulated holes just underneath the gate. That's the reason why this is called the accumulation region. So it's become even more P-type near just underneath the gate. Inversion is exactly the opposite. Inversion is where we drive away the holes and pull in the electrons. All right, give it a second. All right, so this is accumulation. Accumulation happens when you apply negative gate voltage. The side of the band diagram goes down, and the bands curl up like this. Okay, so as a result, in the physical model, we saw that the holes accumulate near the gate. I want you to see in the energy band diagram, same thing. Happens, and it's just explained in a different language. So here you can think about the fact that, okay, you have a P-type material, so you have a lot of holes here, okay? But the difference between this example and the previous example is that you have this slope here. You have a slope in the band diagram. Okay, and as we know, the holes like to go up the slope. Electrons like to go down the slope. So holes that are in this region will get pushed up here by the electric field, and so there will be an accumulation of holes here. So we refer to this type of thing as a potential well. Okay, wherever you have an electric field here, that electric field brings the holes towards the oxides, but then the oxide has this large barrier here that prevents the holes from going any further. So, you know, that's the way that this is described in terms of a diagram. The holes are accumulating in this a potential well. They're stuck in that well. Okay. We'll see an example of another example of a potential well in the inversion, in the case of inversion. All right, so that's, again, just emphasizing the fact that you have this buildup of holes just underneath the gate. Okay, now the depletion. Depletion is when we start applying a positive voltage to the gate, but it's not enough voltage to create a strong inversion effect yet. So imagine that we just apply a small positive voltage on the gate metal. Okay, and so we're going to do the same thing that we did before. So we have our equilibrium band diagram drawn here. This time what's happening is we are applying a small positive voltage to the gate metal. And just for everyone's understanding, I will draw it again here. So P-type substrate, we have an N-type material here. The difference in this one is that we are applying a small positive voltage to the gate. So our VGS is positive, but it's small. So you build up positive charge here. You build electric field is pointing towards this from the positive towards the bottom of the substrate. So this electric field, it drives away the holes, but the electric field is not strong enough yet to pull in the electrons. So if you pull in the electrons, then you've essentially inverted the material. But the voltage that we're applying here is not strong enough to invert the material yet. But it is strong enough to push out some of the holes and create a depletion region. So let's look at what that looks like in the energy band diagram. So this is our equilibrium band diagram. This time we are applying a positive voltage on the metal. So when you apply positive voltage to the left side of the diagram, the opposite side of the diagram, the right side of the diagram, the Fermi level goes up. So you're going to imagine we're going to see this right side of the diagram just all go up together, right? Because everything goes up as a unit. When the Fermi level goes up, EI, EC, EO, and EV, they all go up collectively as a unit. So imagine this goes up here like this. Now you're going to, you can't have a discontinuity in E0 like this. So the bands have to bend. And you can see here that the E0 will bend downward like this so that E0 remains continuous. All right. Because E0 bends downward like this, so does EC, EI, and EV. So all of them bend down like that. Now, just like before, we look at the fact that you have bending in the diagram and think about, okay, what are the carriers doing? Okay, we have a P-type substrate. There's a lot of holes. So we're going to think about that one first. So imagine the holes, there you go. What the holes do in this case is imagine that there are holes everywhere in the P-type material. However, the holes in this region specifically, just near the gate, the slope is going up like this. So holes like to go up the slope. So the holes get pushed away because of the slope in the band diagram. Notice that this is exactly the opposite of accumulation. In accumulation, the slope was going in the opposite direction, and that created a potential well that trapped the holes just near the gate. Okay, by contrast, what's happening in the depletion mode is exactly the opposite. You have a slope that's pushing holes away from the gate oxide. Okay, so these holes go away like this, and that creates a region where there's less holes, and this region is a depletion region. That's the reason why it's called depletion. Remember, anywhere where you have a slope in the band diagram, that means you have an electric field. Okay, when you've depleted the holes away, what you're left with are those immobile ions that have a charge associated with them. Okay, so you created basically like 1/2 of a p-n junction here, the depletion region here. Any questions? Okay. Question, is this conductive? Is there a conductive channel here between the source and the drain?
No.
Okay. Why is there no conductive channel between the source and drain?
Because you pushed the holes away, but you didn't bring any electrons up to create a channel.
Correct. So going from source to drain, you're going from N-type to P-type to N-type. So you have two back-to-back diodes. There's no conductive channel going through there. There's no electrical connection between the source and the drain. Cool. All right. Now we're going to talk about inversion. All right. So we talked about the two other, the two other cases, or the three other cases: equilibrium, accumulation, and depletion. Now, inversion happens when you apply positive voltage to the gate, just like before, in the case of depletion, but we're applying more voltage. We're applying enough voltage that we can actually invert the material. So let's draw it again. So you have your N-type material here, N-type material here, your gate material here. We apply a positive VGS. This time there's more charges on the gate, so the VGS is greater than VT. That's the key thing here. So that creates a strong electric field. This pushes away the holes. Let's erase this. So the holes are getting pushed away. All right, the fact that the holes are getting pushed away means you have a depletion region, but then you also pull in the negatively charged electrons here near the gate. So you've inverted the material. You've created a conductive channel between the source and the drain consisting of these mobile electrons. So what's happening in the band diagram? We apply a positive voltage on the metal. So in relation to the left side of the band diagram, the right side of the band diagram is going to be higher. Okay, so imagine that you have the right side of the diagram. Now the Fermi level is much higher on the right side than it is on the left side. Okay, so it's the same thing as the depletion, except you've applied a larger voltage, so you expect to see more bending. All right. Now, again, you're going to connect the E0s together just like before, but what you're going to see this time is an interesting effect. All right. Now you can see that the bands are bending like this, but there's more bending than there was in the previous case. So there's two effects that happen here. The first effect is what I showed you before, is that the holes in this region, I'll just draw it on there since it's not on there. The holes in this region get depleted away from the gate. But the second effect that happens is that an electron that's in the p-type material, there's enough of, where I'm drawing here, there's a strong electric field here. Strong electric field that will pull the electron in. Just like there's a strong electric field that pushes the holes out, the electrons like to go down the slope in the band diagram. They go like this. Okay? And so as a result, you get an accumulation of electrons here. So this is a potential well that's holding on to those electrons. Okay? So a difference between the depletion and the inversion here you can see that holes were also being pushed away, but there wasn't enough electric field. There wasn't sufficiently a high electric field here to pull in and create a high concentration of electrons here near the gate material. Another way that you can think about that is think about how p-type p-type of material is and how n-type of material may be. So to do that, you just look at the Fermi level and you look at where EC and EV are in relation to the Fermi level. Okay, you can see in this example the Fermi level is there's some distance away from EV and there's some distance away from EC. Okay, so if you look at this diagram, you can see that these distances are approximately equal. That means this material is neither p-type nor n-type. It's very similar to an intrinsic material. Another big hint that you can see there is that you see the intrinsic level. You see how EF is very close to EI here. When your EF is equal to EI, that means you have an intrinsic material. All right, compare that to the inversion mode. Okay, if we were to draw out, if we notice the location of the Fermi level here, okay, zoom in here where my mouse is, the key phenomenon that's happened here, and this is why this is called inversion. Notice that EI has crossed over. It's crossed over EF. Okay, so EF is here, and EI has crossed over it. What does that mean? If EF is above EI, we know this from chapter 3. If EF is larger than EI, if it's above it, that means you have an n-type material. If EF is below EI, you have a p-type material. Okay, out here, if you look on the right side of the diagram, EI is above EF. So this is your p-type substrate material. Okay, but just near the interface, now EF is above EI rather than the other way around. So here, notice that EF is close to EC. It's farther away from EV. So that's the way that you can explain and say, oh, well, if EF is close to EC, if it's above EI, that means we have an n-type material. So just at the interface here, you have an n-type material. Back out here, on the right side of the diagram, you have a p-type material. Okay, so that's how you describe inversion in an energy band diagram. Again, I'll repeat it. I really highly suggest that you go through and you draw the band diagrams for each of these modes for an NMOS device as well as a PMOS device. It's almost guaranteed that you will definitely have a question on the exam that will involve drawing the band diagrams in one of these modes for one of the two types of semiconductor MOSFETs, the NMOS or the PMOS device. Okay, any questions? Okay, let me just check the chat real quick. Let's see if there's any questions. Okay, Llama has a question. You will destroy the insulator and short the metal to p-type.
I think she was just answering your questions in real.
Oh, okay. All right, Llama. Sorry, I missed your answer. Thank you. Sorry, I missed that. Okay, let's continue here. So this is a summary. This is a summary of the NMOS modes of operation. The accumulation mode is where we applied a negative voltage to the gate, and we saw an accumulation of the holes near the gate. Depletion is the opposite, where we started applying a positive voltage to the gate, and we saw the positively charged holes leave this area, and that resulted in a depletion region near the gate. And then in the case of inversion, we also saw the holes leave this area, creating a depletion region. And furthermore, the electrons that were out here, the minority electrons, keep in mind there's very few minority electrons in a p-type material, but when there's a strong electric field, they can all aggregate, they come together in this potential well, and in that potential well, there's actually a high concentration of electrons. So at the potential well, that's where the electrons are now, the material has become N-type. It's switched from P-type to N-type. All right, this is V is less than 0, V is greater than 0, and then V much greater than 0. So this happens when V is greater than VT, threshold voltage. All right, so how much time do we have here? Good. Doing okay on time? Okay, can everyone still hear me?
Yes.
Okay, I thought that I lost my mic for a second there. Okay, thank you. All right, so the next question we're going to get at is, what is the threshold voltage? How do we define strong inversion? Okay, we've just been talking like qualitatively at this point. Now we have to get to the point where we're more quantitative with it, and we want to actually come to a value. How do we calculate what this threshold voltage is? What is that magic number? And so that's what we're going to be talking about in the next few slides. The first thing we're going to do is define what strong inversion is. Okay, and we're going to be defining that in terms of the band diagram. Okay, and there's actually quite an intuitive explanation for this. And that intuitive explanation is phi s is equal to 2 phi f. So I'll explain what that means. Out here in the p-type substrate, this is far away from the gate, you have a distance equal to q phi f. And does anyone remember what that q phi f is equal to? Q phi f. Because this has to do with just the doping of the p-type substrate. So this is stuff that we did in module 3. Okay, just to remind everyone, this is KT ln of Na over Ni. Okay. So the phi f is kT over, q phi f is equal to kT ln of Na over Ni. Right? This is just from the doping. You find the distance between EF and EI. Right? So you have a certain concentration. Based on this, you have a certain concentration of holes. When you get near the gate, what we are doing is we're defining strong inversion is when this distance A, let's say this was B, so when A is equal to 2B. Why are we saying it like that? Like, why is that a good definition? Well, what we're saying is we're trying to create the mirror image of the p-type material. Meaning, like, let's say the p-type material has a whole concentration of 10 to the 18th. Okay, so out here, let's just make up a number and say like the whole concentration equals 10 to the 18th, and of course the electron concentration is equal to Ni squared divided by 10 to the 18th. Okay, so out here we are defining strong inversion. Let's say strong inversion is when N is now equal to 10 to the 18th, and then P is equal to Ni squared over 10 to the 18th. Okay, so we're basically saying like that the material near the oxide, near the gate, has to be the mirror image of the p-type material far away from the gate. So if the p-type material far away from the gate has a whole concentration of 10 to the 18th, then the the material near the oxide has to have an electron concentration of 10 to the 18th. Okay. If the p-type material out here has a concentration of, say, 10 to the 17th, that means that strong inversion would be when the N concentration is 10 to the 17th near the gate. Okay, and so if you have an N-type material with basically the mirror image of the p-type material, then what, in terms of the energy band diagram, what that means is that your EI, the amount of bending in EI, this amount of bending, it has to bend in an amount twice of Q phi F, because we want this distance here. We want the new Q phi F, or let's just say this is phi S, sorry. Here, let me clean this up and explain this. We want this distance here to also be equal to Q phi F. So the amount of bending that we need, this refers to, phi S refers to the amount of bending that we need. This has to equal to 2 times phi F. Okay, that's how we're defining strong inversion. So just remember this formula here. And one thing I want to make sure that we clarify so you don't get confused is that this phi S, I'm not sure why it's referred to as using this S. I think it's a little bit confusing. Don't confuse this. Don't confuse this with the semiconductor work function. They use the same symbol, so that's why it's a little bit confusing. Okay. This is not the semiconductor work function. This is the amount of bending of the band diagram within the semiconductor. All right. Any questions? Questions? Okay. All right. Now we're gonna we've spent time looking at the energy band diagram. Now we're gonna look at the charge distributions when you have strong inversion. Okay, so again we're gonna look at the vertical cross section. So we're gonna start at the metal on the top, and then we have the oxide just below it. Okay, and remember the oxide has some thickness associated with it. So there's a thickness of the oxide here given by Tox, and the oxide also has a property that it has a certain dielectric constant, which is denoted by epsilon ox, epsilon the oxide. Below the oxide, we have the substrate. Okay, so again, we're looking at that vertical cross section, not the horizontal cross section. So we're looking in this region here. Okay. All right, so there's metal, the oxide, which has a certain thickness, and then you have the semiconductor underneath it. The semiconductor has certain properties associated with that as well. If you think about it, what are the things we can control in the semiconductor? Mainly, we have control over the doping. All right, so Na is our doping level, and that's sometimes called N sub for the substrate doping. So the two are equivalent to each other. Just remember that. So based on the doping sets the semiconductor work function. It sets the phi F that you saw on the previous slide. It sets the band gap. The band gap is determined by the material, and the dielectric constant is determined by the material that you use. Okay, so these two are determined by doping. These two are determined by the material. So now when you apply a strong gate to source voltage here, and let's say your VGS is greater than VT, so that you have strong inversion. These are what the charge distributions look like. We're going to actually like label them and calculate them. Sorry, I have to do this. It's a little annoying, but just wait for a second here. There we go. Okay. So you have, again, we've talked about this a bunch of times already. You have a positive charge buildup on the gate when you apply a gate voltage greater than the threshold. You have an electric field that's going through the oxide, and it actually penetrates into the semiconductor as well. I haven't drawn the field lines in the semiconductor because it'll just clutter the diagram, so I'm just drawing it in the oxide. But there is a strong electric field in the oxide. Now that electric field does two things. It drives away the holes. Okay, when you drive away the holes in a p-type material, you're left with the depletion region, which is a series of negative, immobile, negatively charged ions. So this would be like the column 5 ions, like phosphorus, for example. And these are bound, so they're not mobile. They can't move. The second effect that happens is that you pull in the mobile electrons, and those are denoted by here, as you can see up here. Q sub S refers to as the surface charge, and Q sub D refers to as the depletion charge. This is a subtle but important point, is that notice that the surface charge is just underneath the gate. It's packed very close to the surface of the oxide material, whereas the depletion charge can extend several microns into the semiconductor material. That's why it's denoted as Q sub S. All right. The reason it's denoted Q sub S, the reason the electrons can accumulate like that is because the electrons are mobile. So the electrons want to keep moving opposite the electric field. The electric field is pointed from top to bottom. As the electrons, because they're mobile, they can push as far as they can towards the against the direction of the electric field. So they can accumulate here like that. Whereas the depletion charge is immobile. It's immobile, so it maintains a certain density and spacing between these immobile charges, and that's determined by the doping density of the material in the semiconductor. Okay, so we are going to calculate this distance here, the depletion width. Okay, this turns out that this is a pretty important number, and that's denoted as WD. This table is here for to help you on the homeworks and just to give you some clarity on the symbols, because there's a lot of symbols here, and it's sometimes hard to keep them all straight. So I've just created this table here so that you all understand what the different parameters are. Phi m refers to the metal work function. Epsilon oxide is the oxide dielectric constant. So every dielectric material, every insulating material has a dielectric constant associated with it. So the dielectric constant for a material is equal to epsilon epsilon 0 times epsilon r. Epsilon 0 is a constant. I'm just going to put it in this other box. 8.85 times 10 to the negative 14 farads per centimeter. That's epsilon 0. Epsilon r depends on what material you're at. So silicon dioxide has a relative dielectric constant of 3.8. For silicon, the material down here in the substrate, that has a dielectric constant of 11. All right, these are parameters that will be given to you. Phi f, I showed you how to calculate that on the previous slide, is equal to kT over Q ln of n sub over Ni. And that's given in volts. So the substrate doping. The semiconductor work function, which is the distance between the Fermi level in the semiconductor to the vacuum level. So I'll draw that here just to remind everyone. E0 and you have EC, EV, and then your Fermi level, depending on whether it's N-type or P-type. This is the semiconductor work function. Okay, and that can be calculated as, according to these formulas, where X sub S is the electron affinity, Eg over 2, that's a band gap over 2, and then plus or minus Q phi F, which is what you calculated here. The plus or minus depends on whether you're an NMOS device or PMOS device. Okay, the next thing here is a formula. You're going to be calculating all these. That's why I'm going over these in detail. The WD is the depletion width, the width of the depletion region here. Now, this is one of the formulas we're just not going to bother deriving, but it's derived in a way that's similar to how the depletion width is derived in a PN junction. We're just leaving that out here just in the interest of time. But you can see here that it's equal to 2 times the square root of this function. And what's on the numerator of the square root is epsilon s and phi f. So on the denominator, there's q times n sub. So depending on, it's mainly controlled by the substrate doping. Okay, if you increase the substrate doping, then the depletion width goes down. All right, and that kind of makes sense. Just think back to the PN junctions when you had a highly doped diode. If you had a highly doped diode, the depletion regions tended to be smaller. Okay, same thing here. If you have a highly doped substrate, then the depletion region in the substrate is going to be smaller. And then finally, there's an equation for the depletion charge. The depletion charge is the total amount of charge that you have down here. It's given in coulombs per centimeter square. So charge per unit area. Okay, because obviously the larger the area of the gate, the more charges you're going to have. All right. So this is what the charge distribution looks like in a MOSFET at strong inversion. Now, if you remember what we did for the PN junctions, then we first found the charge distributions in the depletion region in a PN junction, and then we said, okay, now we're going to find the electric fields in the depletion region, and just outside the depletion region, we're going to find the charge densities everywhere. We're going to find the electric fields everywhere, and eventually we found the electrostatic potential everywhere in the junction diode. We're going to do the same thing here, following the same process. This is just the energy band diagram at strong inversion, but this is, you remember the first step that we started off with when we figured out the electrostatics of the diode? We started off with the charge density. Okay, in the case of a PN junction, you had a positive charge density on one side, a negative charge density on the other side, and they both look like squares. Here it looks a little bit different. I'm just going to zoom in here. So what we're looking at here is the charge density as you go from the metal to the oxide to the semiconductor here. So keep in mind this X distance, I mentioned this many times already, but mention it again. The X distance is going from the metal through the oxide into the semiconductor. We drew our energy band diagrams this way, and we're also drawing our charge densities this way. So in the last slide, we saw that there's a strong positive charge buildup in the metal. So that's what you're seeing here. This Q is on the y-axis here. This is the charge per unit area. So the fact that this function goes up like this means there's a strong, there's a lot of positive charge buildup near this side of the gate. Okay, and then you have two types of negative charges that build up on the other side of the gate. This is the depletion charge. Depletion charge has low density, but it has a large width. All right, so large width, low density, and then at the surface, this is labeled Qn, but it's equal to Q sub S that you saw in the previous slide. It's a surface charge, and you can see that there's a very high density of negative charge just near the gate. And so that is your inversion channel. this area does not conduct. This does not conduct here. This is the depletion region, which consists of negatively charged immobile ions. This portion here consists of negatively charged mobile electrons, and this is what allows electricity to be conducted from the source to the drain region. All right. Some details here. This is the width of the depletion region. So from the charge density, we can figure out what the electric fields are. And I'm only going to go over it qualitatively, but I think it's important that you understand it. In order for us to go from charge density to electric field, we said that the electric field is equal to the integral of the charge density. So if you remember what we did in the diode chapter, we said like the electric field at some point x, we have to take the integral, of charge, everything to the left of that point. So imagine our x moving in this direction. Okay, as we move through this large area of charge, the electric field is going to increase. So notice that the electric field increased here suddenly. Okay, so that if I drew the electric field on this plot, it would just go up very suddenly here, and then it would be constant like this. So this is the electric field. And that's the same thing that's shown here, okay, on this right diagram. So the electric field goes up suddenly because of all that positive charge, and it's constant across the oxide region. Okay. Remember I said before that there's a strong electric field in the oxide? That's what's shown here as well. Strong and uniform electric field in the oxide region. This is the oxide, this is the metal, and this is the semiconductor. Now, on the other side, the first interesting feature you'll notice is that the electric field drops suddenly here. The reason it drops suddenly is because of this inversion channel. Here, it's on the left. So whenever you have negative charge, that will drop the potential. Wherever you have this positive charge, the positive charge increased the electric field, and the negative charge puts the electric field in the opposite direction. So the electric field drops suddenly because of all that negative electron surface charge, and then it drops more gradually as you're moving through the depletion region. So the depletion region, as you know, is here. It's a low concentration of negative charge, and so that causes the electric field to decrease at a slow rate. Okay, we have a formula for this W, and that was shown on the previous slide. It's 2 times epsilon phi f divided by QNA, the square root of that quantity. Okay. Now, once you have the electric field diagram like this, the important points of here to notice is that the strongest electric field occurs in the oxide. Okay, and this turns out to be an important point for scaling the transistors. When your transistors become smaller and smaller, it turns out you have to make the oxide at a lower thickness, and that increases the electric field in the oxide greatly, and that results in an effect called charge leakage, and in some cases failures of the gate. So you have to be careful about that. The strongest electric field occurs in the oxide. It drops suddenly here and then drops more gradually across the depletion region. The final part here is the electrostatic potential. So we talked about the electric field. Again, if you integrate the electric field, you'll get the electrostatic potential. Okay, you have to integrate it and also invert it. In the interest of time, I'm just going to explain this kind of qualitatively. Excuse me. So wherever you have electric field, the electrostatic potential V is the integral of the electric field. V is equal to the negative integral of E of x dx. So you're integrating this function to get the voltage function. and you have to negate it as well. So when you do that, you see that this region of oxide, where you have a strong electric field, that's going to cause a voltage drop here. Okay, so there's some voltage drop that occurs across the oxide, and then the remaining voltage drop occurs across the semiconductor. So it occurs like across the depletion region like this. Okay. So what we're going to do next is we want to calculate this V when you have strong inversion, so we can figure out what the threshold voltage is. So that's what we're going to do. What we're going to do is we're going to figure out how much voltage drops across the oxide, and then we're going to figure out how much voltage drops across the semiconductor. That's what's shown in this formula here. Let's see, how are we doing on time? Okay, we got about 10 minutes left. We can cover this. Okay, so with threshold voltage, there's three parts that are used to calculate the threshold voltage. There's a flatband voltage. That's the third one. The second one is the depletion charge, and then there's the bending in the semiconductor. So if we put this in the context of the previous diagram, this 2 phi f term, okay, this 2 phi f term corresponds to this. So the 2 phi f is the amount of voltage potential drop across the semiconductor. Okay, so what I mean by voltage drop is this. You know, you have this is your gate material. So you have a positive VGS being applied here, and then you have your substrate here. So up here, the voltage is going to be equal to VGS at the top here. In here, the voltage is going to drop. There's going to be some voltage drop across the, oh, I'm sorry, I didn't draw that right. The voltage drop occurs across the oxide, so let's draw that. So the oxide here. All right, so the voltage is maximum up in the metal. It becomes lower and lower as you go across the oxide, and then it drops a little bit in the semiconductor depletion region here. And so by the time you get to here, the voltage is already 0. So most of the voltage drop occurs in this region here that I just highlighted with the pen. So we're just going to calculate what the voltage drop across those regions are. This is the voltage drop across the semiconductor. This is the voltage drop across the oxide. Okay, I'm going to label this as well, just to make the connection. Voltage, this is the voltage drop across the semiconductor. And then this is something called the flatband voltage. So let's start with the strong inversion part of it. So the MOSFET is considered to be on when the gate voltage is greater than the threshold. That's where we're interested in calculating this. Now, in your, maybe in some of your undergraduate classes, you didn't actually calculate the threshold voltage. It was given to you in a problem, but for this class, we will calculate the threshold voltages. The first part of it is what I mentioned earlier, so I'm not going to spend time on this. Like, there's a voltage drop across the semiconductor due to strong inversion. I already went over how to calculate phi f and then calculate the amount of bending as 2 phi f that you see here. The second portion is a voltage drop due to the depletion charge. This voltage drop occurs over the capacitor, and this is all the same stuff that you saw earlier. You have this depletion charge here, and then you have this positive charge up here. So this looks exactly like a capacitor, Positive charge buildup on one side, negative charge buildup on the other side. The voltage drop in a capacitor, as you know, the relationship for a capacitor is Q equals CV. So the voltage drop across a capacitor is equal to Q over C. And that's where this formula essentially is coming from. So Q is the amount of charge here. So it's QM and QD. They should be equal to one another because there's a positive, and the amount of positive and negative charges are equal to each other. But keep in mind there's also a surface charge here, but we're just going to ignore that for the time being. Because most of the charge is due to the depletion charge. So we're going to say here, if V equals Q over C, so we say that the depletion, that voltage drop across the oxide here, across this capacitor, is equal to Q over C. So the depletion charge, QD, divided by CI. Now, CI is the capacitance of the oxide region, of the oxide layer, and that's a unit capacitance. So the CI is equal to epsilon over D. If some of you remember, if you've taken courses before, you know that capacitance for a parallel plate capacitor is equal to epsilon A over D. Okay, but we want to do some of these things in a sort of a dimensionless form, or a form that doesn't require us to also know the area of the MOSFET, because the area could change depending on what the designer does. So we're giving a unit capacitance here. So the unit capacitance here is going to be in farads per centimeter squared. So this is given in farads per centimeter squared. The depletion charge is given in coulombs per centimeter squared. All right, so as a result, the coulombs per centimeter squared divided by farads per centimeter squared cancel, and you're left with coulombs divided by farads, which is a volt. Essentially, it's a volt. All right. So 2 slides earlier, you had some formulas that allow you to calculate what QD is. Okay, so you can calculate QD. You can calculate CI because this is equal to epsilon over D. And I'm sorry for this. The thickness of the oxide is equal to D. So I just want to make sure you all understand this is the same thing as Tox. It's the thickness of the insulating layer. Okay. So that's how you calculate the voltage drop due to the depletion charge. All right. And the last part is the voltage drop due to the flatband voltage. All right. Now the flatband voltage is it's actually due to 2 different effects. The first is the metal and semiconductor work function, and the second is something about the trapping of charges in the gate oxide. And I'll talk a little bit about both. Let's do the first one here. I mentioned when we did this slide up here, the equilibrium band diagram. Okay, so when we drew this band diagram, you notice that this phi m and phi s, these lines are both equal to each other. The lengths are the same. So that means phi m is equal to phi s. And you notice that the band is flat. The E0 band is flat across, and there's no bending in E0. Similarly, there's no bending in EC, EI, or EV. So if phi m is equal to phi s, then the flat band voltage, then you're going to get a flat band when you don't apply any voltage to the system. At equilibrium, you're going to get a flat band. But what if phi m is not equal to phi s? Right? If phi m were not equal to phi s, you could end up having some bending in the band diagram even when you don't apply a potential. You know, if this side of the band diagram moves up, then you'd have some downward bending in the band diagram. And if in the other case, if this side of the band diagram moved down, so if phi m was less than phi s, then you'd have a downward bending here. And you would not have a flat E0 band. What that means, if you don't have a flat band, that means you have electric field just under the gate. And if there's strong enough electric field, you can have an inversion channel even at zero potential. Even when at equilibrium, you may have an inversion channel. And that's where depletion mode devices can come about. Okay, if you have a non-zero flatband, meaning if your phi m is not equal to phi s. All right, so this is what's being shown there. So this is an example, one example, okay, when phi m and phi s are not equal to each other. So in this case, phi m is much less than phi s. You can see that this is the q phi m line, and this is the q phi s line. When you draw the equilibrium band diagram, notice that the Fermi level is going straight across like this, okay? But the E0s, this is the E0 for the semiconductor, and this is the E0 for the metal. Notice that they're at very different potentials. So as a result, there's a bending in the band diagram. There's a bending in EC, and then there's a bending in EV, and that's what causes this effect to happen. So you can actually end up with an inversion channel even when you don't have a potential applied to the gate. And this would be an example of a depletion mode device. A depletion mode device has an inversion channel when you don't apply potential to the gate. All right, so that's the first part here, the phi m minus phi s. The second part, this is an effect that can happen with when you have unclean processes. So this is a diagram that's showing when you have trapped charges in the oxide material. Okay, and you see all these positive charges here. Now you're probably asking, like, why, what are those positive charges? Where do they come from? These positive charges are referred to as a mobile ionic charge, and these are charges that you don't want to have in your system, but can get into your system if your manufacturing process is not clean. This happened to be actually a big issue back in the day with semiconductor fabrication. It was one of the big challenges that had to be solved before semiconductors could be made reliably. There's a process in semiconductor fabrication called wet etching, and there's also a process called rinsing after you do your photolithography steps. So these are both steps where the semiconductor material, the wafer, has to be placed in a liquid. It has to be, and that liquid could be a chemical etchant, which removes oxide, so it's some type of acid, or it might be a photoresist remover, which is also an acid or base type material that is used to remove photoresist after a photolithography step. We don't have time to go into all the details of that, but the key point that I want you to know is that these were all liquid processes, and if the water in those processes that were used were not clean, let's say you use like city tap water instead of deionized water. City tap water, if you measure it, you'll know that it has a lot of different ions in there. It has calcium ions, it has magnesium ions, and so forth. And those ions can actually bury themselves into the semiconductor and get stuck there. And what happens is that they actually get stuck inside the gate oxide. And whenever you have positive charges in the gate oxide, that alters your electric fields. Because as you know, wherever you have positive charges, you end up having electric fields going away from the positive charge. And so that also alters your electrostatic potentials. And so, again, just so you see the sequence of events, let's say you had an unclean process, you were using like tap water to rinse your semiconductors. Ions from the tap water got into your oxide. The positive charges in the oxide create an electric field, and that electric field alters the potential across the oxide, and that potential alters the threshold voltage. So your threshold voltages would change here. And if you think about this, this was a really difficult problem to deal with when wet etching processes were used, because the amount of charges that would get buried in the oxide was very unpredictable. One day your water might be a little bit cleaner than the next day, and one day your transistors have a great threshold voltage and the next day they don't. Another thing that can happen is that the transistors on one side of your wafer have a threshold voltage of 1 volt, and the transistors on the other side of the wafer have a threshold voltage of 0.3 volts. So this could be like disastrous if you're trying to put a billion transistors on a chip. So it was only when this process was solved. In fact, nowadays, a lot of semiconductor processes use dry etching instead of wet etching processes to avoid this very problem. But what this does to the threshold voltage is that it alters it by an amount equal to Q over C. And where is this coming from? It's, again, this relationship Q equals CV. So the voltage drop across a capacitor is equal to Q over C. And so if you have extra charges, if you have extra positive charges inside the gate, the voltage drop that they'll cause is equal to Q over C. So Qi is the amount of dirty charges that you had in the gate, and then Ci is the unit capacitance that we calculated on the previous slide. So both of these effects, the phi m minus phi s, and then the charges trapped in the gate will both cause the band to become unflat. And the way that it was done before is that you would actually apply a certain gate voltage. You apply a certain gate voltage to flatten out the bands so that you don't get any electric field, you don't get any depletion region within the gate, and that's how you determine what your flat band voltage is. Now, for the purposes of this class, I would give you what the density of trapped charges are, or I would give you phi m and phi s and ask you to calculate the flat band voltage. Okay. Typical values of phi ms have to do with the doping of the polysilicon gate. As many of you know now, that you know that the source and drain regions here, there's a gate oxide material here, and then on top of that, the gate material is polysilicon. Okay, polysilicon has a certain metal work function, and then there's a semiconductor work function in the gate. So this has a phi m associated with it, and then the semiconductor has a semiconductor work function phi s. And so the phi m minus phi s is what you're going to be using to figure out your flat band voltages here. And so when you have a polysilicon gate, I will provide you a chart like this that tells you what the flat band voltages are, or what phi ms is as a function of doping. The intuition that you want to remember here is that as your semiconductor doping increases, that's going to increase your semiconductor work function in a p-type substrate, and it's going to decrease your semiconductor work function in an n-type substrate. And as a result of that, the phi m minus phi s will increase with doping in an n-type material, an n-type substrate, and it'll decrease. The phi ms will decrease with doping in a p-type substrate. Okay. So this type of chart would actually be provided to you, but this gives you an idea of how the phi ms changes as a function of doping. And the last slide we'll end with here today is the typical threshold voltages for the conventional NMOS devices. You see that here that it's actually plotted versus doping. And the reason why it's plotted versus doping is because this is the most important parameter in determining the threshold voltage of a MOSFET. If you think about it, if you look at some of these diagrams here, that we drew where we figured out the threshold voltages. Sorry, let me just back. Yeah, look at one of these diagrams here. What do we really have control over? We can control the thickness of the gate oxide, and then we can control the doping of the substrate here. Those are the two biggest tweaks that we have at our disposal. The thickness of the oxide doesn't really change the threshold voltage significantly. I'm just bumping up ahead here, just a second here. The substrate doping impacts it pretty strongly. So in an N-channel device, the threshold voltages will increase with doping, and then in a P-channel device, the threshold voltages will decrease with doping. Okay, and again, this type of chart would be given to you. Okay, so what I expect you to be able to do for the exam, I'm just going to back up here and go to this slide. I want you to be able to calculate the threshold voltages for typical conditions in a MOSFET device. Now, you would be able to calculate the flatband voltage. You'd be able to calculate the voltage drop due to the depletion charge, which occurs across the oxide, and then the voltage drop due to the strong inversion, the bending of the semiconductor. Okay. So I'll post some of the problems up on Canvas tonight. So please give them a try and look over some of the solutions for the diode chapter before next week, so that you can spend time on your projects and have a good head start in prepping for the exam before that last week of the semester when things get really crazy with the project and the exams. Okay. All right, so sorry I went a few minutes over here. Thanks for your patience here. So we will not have class on Wednesday. I hope all of you have a very happy Thanksgiving. Get some, good food and relax. Are there any questions that you'd like to go over before we end the class today? Okay, I see some people commented yes. I think that must have been for a question I asked earlier. Sorry about that. So any questions that we want to go over before we end the class today? Okay. All right. I'll take that as a no. Good luck in prepping for your final projects in the exam, and have a wonderful Thanksgiving holiday. And I will see you all next Monday on campus. We'll have a regularly scheduled class session at the regular time. All right. Thanks, everyone.
Happy Thanksgiving.
Happy Thanksgiving.